Okay. All right, so here's what we want to do. We want to find the derivative, dy dx, the slope of the tangent line to a polar graph at some given point. So if we're given r in terms of theta, okay, problem is to find dy dx. Here's what we have to do. Believe it or not, what we have to do is change the polar form to parametric form. Once it's in parametric form, then we can find dy dx by using the chain rule. Okay? So, dy dx is equal to dy d theta over dx d theta. That's the chain rule. But what is y equal to? Y is equal to r sine theta. And here's r. So what we have to do is take the derivative of r.
But how do we know it's equal to r sine theta?
Because that was changing from polar coordinates to rectangular coordinates. X equals r cosine theta, and y is equal to r sine theta.
Right here.
Yep. So r is f of theta. So y is going to be f of theta sine theta. We're going to have to take its derivative with respect to theta. The x is r cosine theta, so that's f of theta cosine theta. Okay? And we'll have to take that derivative with respect to theta. Let's do an example. Okay? You really don't have to memorize this, but you do know how to change. You do know how to know how to change from polar to parametric. So let's do a problem. Let's do, well, I'll tell you what. Let's do the cardioid. R is equal to 1 plus cosine. Okay. We know what this cardioid looks like. Looks like this. At least some, geez, I'm always short on the bottom part, though. All right, but anyhow, we want to find the derivative dy dx at any given point. So we can find the slope of the tangent line. In particular, let's find the slope of the tangent line with theta is equal to pi over 4. Okay?
Move it over a little bit.
Okay, so let's do it. First thing to do is change from polar form to parametric form. So y is equal to r sine theta. That's equal to 1 plus cosine theta. That's the r. Sine theta. X is equal to r cosine theta. That's equal to 1 plus cosine theta cosine theta. And if in Mathematica, and I'll do this in a minute, I were to do a parametric plot of these equations, we would get that same cardioid that we got from this polar plot, 1 plus cosine. Okay? All right, here we go. This is not pleasant, but we can do it. dy dx is equal to dy d...
How y become 4 cosine?
Yeah. It's not 4 cosine, it's 1 plus cosine.
Oh,
I thought that was 2.
What?
It looks like
Oh, no, this is a 1 plus cosine. I had the 1 here, and I put the parentheses, and I made it too close, so it's...
It's all right. It's kind of like a 1. Alex, you can...
Okay. All right, it's dy d theta over dx d theta. All right, we have to do dy d theta. It's a product rule. It's first times the derivative of the second plus second times the derivative of the first all over dx d theta first times the derivative of the second plus second, holy moly, times the derivative of the first. Okay, so wow. This is not nice. That's equal to cosine theta. I don't know if multiplying it out is, well, I guess it's worthwhile. It's cosine theta plus cosine squared theta minus sine squared theta. Unfortunately, we got a minus there, which is not a good thing. Down here, we got a negative sine theta minus sine cosine minus another sine cosine minus 2 sine cosine. Holy mackerel.
And some of these kind of look like identities.
Yeah, they look like they should be, shouldn't they? But, you know, cosine squared minus sine squared is an identity. It's cosine 2 theta. It's a double angle identity. Okay? And the 2 sine cosine is another double angle identity. It's sine 2 theta. We could rewrite it that way. I'm not sure how much we're gaining, but let's do it. Cosine 2 theta. Down here we got an opposite of sine theta minus sine 2 theta. Oh boy, this is not nice at all. And if we want the slope of the tangent line at theta equals pi over 4, we're going to replace theta with pi over 4. So here's what we're going to get. You ready? We're going to get dy dx is equal to cosine of pi over 4 square root of 2 over 2 plus the cosine of 2 times pi over 4 is the cosine of pi over 2. What's the cosine of pi over 2? Zero. That way. That's nice. And then we have a negative sign, or the opposite of sine of pi over 4. It's a negative square root of 2 over 2. And then we have the sine of 2 theta. And if theta is equal to pi over 4, 2 times that is sine of pi over 2. And what's the sine of pi over 2? 1. So we got minus 1. So I end up with square root of 2 over 2. And I get negative square root of 2. I'm going to put this over 2. I'm going to multiply this guy by 2 over 2. Get over 2. And then I'm going to multiply numerator and denominator by 2. I'll have the square root of 2.
Wait, why is it minus? Oh, because you multiplied the 1 by, okay.
Okay. And then I'll have a negative I can take out, and then a square root of 2 plus 2. Oh, boy, that is just plain not nice. That is a total surprise to me, too. Okay, but whatever. What it's telling us is that is the slope of the tangent line to that graph at theta equals pi over 4. It's a negative slope. It's sloping downward, which looks to be reasonable. Okay? All right. Any questions on that?
So that's the final answer, negative square root of 2
Yeah,
over
that's
square
it.
root of 2 plus
That's
2.
it. Hey, that's what it is. Now, it would be nicer if we had to find the slope of the tangent line at theta equals 0. What's the slope of the tangent line at theta equals 0? Now, think of the cardioid again. At theta equals 0, I'm at this end. What's the slope of that tangent line? It's undefined. It's a vertical line. And what we put in a 0 in here, what happens is we get a division by 0, and we do get undefined. Okay? When we put the 0 in here. Yes, because you can't divide by 0, so you get undefined. So at least it conforms to what we think it should be. Okay? All right. One other thing we have to do with polar coordinates, and that's to find their area. Okay? So let's do it. Area of polar coordinates. And what we're going to do is stay in polar coordinates to find the area. We're going to derive a formula that is in polar coordinates. Let's say r is a function of theta. And what we want to do is find the area bounded by, let's say, theta equals theta sub naught to theta equals theta sub 1. We want this area here. Okay. Well, think about what you did in rectangular coordinates to find the area under a curve. You divided up the x-axis into little pieces, little delta x's. You found the area under the curve over each of those delta x's. Use rectangles, okay? Where the area of each rectangle is equal to the value of the function, the height of the rectangle, times the delta x, and sum them all up. You ended up with, what did you end up with? What's it called when you end up with a... Thank you. It's a Riemann sum, anyway, Kev. And as long as you get a Riemann sum, you can evaluate it with an integral. That's what integrals do. They give you Riemann sums, okay? They evaluate Riemann sums for you. Go ahead.
Is that a V equals F, or is that a...
That's an R.
That's an R.
It's an R. It looks like a V, but it's an R. Well, we're going to do the same thing here. We're going to divide this up into little pieces. Okay. These little pieces will be delta thetas. What we want to do is get an approximation for the area of the sector that's defined by this delta theta. Now, we can go out along this R or this R and make an arc of a circle. Let's take this R here. This is similar to the process of using left endpoints or right endpoints for the rectangles. It just doesn't matter which ones you take because you're going to let the number of them go to infinity and the delta x's went to 0 and these delta thetas will go to 0. So here's my question. What's this area? What's the area of this piece right in here? That ith area is going to be approximately, it's the area of the sector that's defined by a delta theta and an R. Let's call this R, you can call this, okay, f of theta sub I, say. Okay, this distance right here is R sub I, or f of theta sub I. What's the area of a sector of a circle whose central angle is delta theta, whose radius, in this case, is going to be f of theta sub I. That'll be this distance here. What's the area of a sector? How do you find the area of a sector?
Arc length.
What's that?
Arc length and R.
You need R. Okay, here we go. Watch this. Okay, you're on the right track, Kevin, in your thinking, which is always a good thing. What's the area of the whole circle of radius R?
Pi r squared.
Thank you. It's pi r squared. The area of the circle defined by this R is going to be pi f of theta squared. F of theta is our R here. Okay? But now we've got a piece of it. We've got a piece of it. That piece has a central angle, an angle of delta theta. Bless you. What fractional part of the circle are we talking about if we have a central angle of delta theta?
Is it theta over 2 pi times r squared?
Okay, that's pretty good. That's not bad. What it is delta theta, that's our angle, over 2 pi. 2 pi would be the whole circle. The part of the circle we're talking about here is the delta theta over 2 pi. 2 pi being the whole circle. In other words, if I had a quarter, if I had a 45-degree angle here, I'd have a pi over 4 central angle. And what part of the circle am I talking about with an angle of pi over 4? It'd be pi over 4 over 2 pi. Okay? It'd be pi over 8. It'd be 1/8 of the circle. That's a 45-degree angle would be 1/8 of the circle. Okay? Pi over 2. If I had a pi over 2 angle there, I'd got a quarter of the circle. Okay? All right? It'd be 1/4 of the circle. All right. So that's the part of the circle. The whole circle is pi r squared. Okay? This is that piece of area right here. The whole circle times the part of the circle we have. The pi's will cancel. I've got 1/2 f of theta squared delta theta. That's that little piece. What's the approximation for the area of the circle? Area bounded by these two lengths here? It's the sum of all these. Add them all up. Okay. In terms of n, we'd have this.
Delta n or a n?
A sub n.
Okay, it's
Yeah, that's the area in terms of n of these pieces. If I make the delta thetas all the same, I don't even need a delta theta I. And what's the exact area then? It would be the limit as n goes to infinity of all this. I could have taken the 1/2 out front. Okay, let's take a look at this. What do I have here with that limit of that sum? We can integrate it. We can evaluate it with an integral because we have a Riemann sum. It's a Riemann sum in terms of theta. We have the 1/2. Who cares? We can take the 1/2 constant out front. We have a function of theta squared. But I'll tell you what. If our function of theta is continuous and differentiable, so is our function squared. And we have a delta theta. Those are the ingredients for a Riemann sum. The area, therefore, of a polar graph is... How much time? The area of a polar graph is equal to 1/2 the integral from a to b of f of theta squared d theta. Okay, that's it. Comes directly from our what we just
Is
did.
it b over it? Is that b on the top there?
Yes, it is.
Okay.
Yes, it is. All right. Let's see. We could do a problem. You ready? Let's do a problem. Let's do r equals cosine theta. Okay. Let's find the area. R equals cosine is this. Okay. It's a circle. The radius of this circle is what? One. No. 1/2. Thank you. Okay. The area of this circle is going to be pi r squared. R is 1/2. It's going to be pi over 4. Let's do it. Let's do it with polar coordinates. The area is 1/2. Now, you got to be careful, like I mentioned the other day. Well, you don't want to go around 0 to 2 pi because that traverses the circle twice. Let's go from here to here. 0 to pi over 2. That'll give us half the circle, so we're going to multiply by 2. Okay? R squared. This should give us the area of this circle. Okay? 1/2 f of theta squared. I'm going to multiply by 2 because I'm going to go from 0 to pi over 2 and only take the top half. And that means I'll double it. All right, how do you integrate cosine squared? What do you do? How do you integrate cosine squared? Yes, yeah. Yeah, yes.
Cosine theta and then sine theta times sine theta.
Cosine squared theta.
Cosine squared is equal to 1/2 1 plus cosine 2 theta.
Wait, why is the 1/2 on the other side? No, we just canceled that out.
We just canceled. I just put another one in because that's the half angle formula for cosine squared.
Okay.
Okay? That's how you integrate cosine squared. That's how you integrate sine squared. You replace it with a half angle formula. The cosine squared is a plus. The sine squared is the minus. That's a Calc 2 thing. Remember that thing for Calc 2?
Yeah, so you change, okay, so you do
Yeah.
double angle.
Yes. Well, it's a half angle, really, but it looks like it should be called a double angle. But double angle is a little bit different. All right, but that's what the substitution is. Let's do it. The integral of 1 d theta is theta. The integral of cosine 2 theta, cosine u form, u is 2 theta, du is 2 d theta. Multiply by 2, multiply by 1/2. Okay? The integral of cosine is sine. Okay? That's what you get. The integral of 1 is theta. The integral of cosine 2 theta is 1/2 sine 2 theta. Substitute in pi over 2. You get pi over 2. Substitute in pi over 2. 2 times pi over 2 is sine of pi. Sine of pi is 0. Forget about it. Substitute in 0. 0. Substitute in 0. Sine of 0, 0. We get pi over 4. Which is exactly what we said we would get. Okay, so here's what we have. We're going to do a little bit more polar equation. What's today? Wednesday?
Yeah, today's Wednesday.
I said I would finish on Thursday. All right, forget everything I said today.